Hey guys, this is a 3D scan of the center console from a 2008 Ford Mustang GT sent in by one of our viewers. This scan was captured with the Creality Raptor Pro. It was made using two passes, front and back, then merged together. The scan quality is excellent. Over 95% of the surface area was captured. The Raptor Pro has become one of the most widely used scanners in this community for automotive part 3D scanning, based on the number of reverse engineering scans that have been sent to me. In this video, I will show you how to reverse engineer this console bezel using BricsCAD. You might be wondering why we need to convert the scan data into CAD when the scan already looks nearly perfect. The bezel on the right is the reverse engineered CAD model. CAD produces smoother, sharper corners, and you will really notice the difference once it's 3D printed. This part is quite intricate, so it's best printed with a resin printer to really showcase those advantages. Reverse engineering in CAD also lets you adjust the mounting to fit different instruments, but in this video I'm not making any modification. This bezel required quite a bit of CAD work. We'll be using nearly all of BricsCAD modeling commands, so I think you will pick up a lot from this video. A big thanks to the viewer who commissioned me to reverse engineer this part and also allow me to share it as a tutorial so we can all learn together. At the end of the video, we will also check out the 3D printed result from the K2 Plus. This part measured 30 by 30 cm and it nearly maxed out the printer's build volume. The hardest part for reverse engineering is getting started. The console panel already has cutouts for the instruments, leaving very little surface to trace. I will create two cross-sectional profiles, one along the edge and one in the center, then mirror one of them to the opposite side. With these three profiles, I can build a 3D spline to reconstruct the panel surface. The side brackets are also tricky to model. They were created from a different plane than the main panel and then welded together. On the back side, there are ribs that run along the curved surface, and we will go through how to model them. Some of the instrument mounting brackets are also built from different planes. This mounting bracket for the audio system is especially tricky to model. It steps down in sections, and one of those steps has curved surface on both sides. Here's in BricsCAD. I will provide the point cloud download link in the description in case you would like to follow along. This part isn't easy and isn't really suited for beginners. You will need some background in CAD modeling to keep up. First, I will align the point cloud to the X, Y, and Z axis. I will do this by drawing straight lines along the edges of the scan data, then using the align command with two pairs of reference points to snap them to the horizontal and vertical axis. Next, I will create a midpoint between these two lines and move the center to the origin. To check the accuracy of the mirror plane, I will mirror one of the holes to the opposite side. Once you have aligned the point cloud, it's a good idea to copy its orientation coordinates into a notepad. That way, if you accidentally delete it during the project, you can restore the point cloud to the exact same orientation. Next, I will draw a straight line along the side of the panel and crop the point cloud along that line. Then I'll use the UCS Z-axis to reposition the plane and rotate it 90 degrees along both X and Y axis to create the sketch plane. Next, I will trace the closed loop sketch profile using polylines, then apply the Add Pouch command to transform the straight segments into smooth curves. Next, I add ribs along the bottom of the profile since they also run across the panel. Next, I will create a second sketch profile at the center of the panel. Since most of the surface has already been cut out, I will copy the first sketch profile, flatten it onto this sketch plane, and then modify it. Next, I will align the flattened sketch to the remaining point cloud, then cut and trim the lines and adjust the curves at both ends. Next, I will mirror the first sketch to the opposite side. That gives me 3 points I can use to create arc rails. Next, I will use a spline to create the arc rails, then break it at the center since I'll be lofting only 1/2 of the panel. I have added a total of 11 guide rails to force the surface to curve smoothly. Now the original panel surface has been fully reconstructed using the loft command. The side bracket appears to have different lengths, and when I mirror the line to the opposite side, the top brackets don't match. So I will model the left side, mirror it, and then modify it to fit the right side. I move the UCS to this side of the panel, modify the first sketch, and then create an extrusion. I will extract the line, offset it, and then use the push-pull command to cut a step profile, and then I will fillet the corners. Next, I move the UCS to the tip of this line to set up a new sketch plane, and then I will trace the bracket profile. This bracket will be extruded parallel to the original X-axis until it extends past the panel edge. Then I will use the slice command to trim the bracket flush with the panel. Then I will use the push-pull command to extend the face outward until it aligns with the point cloud. Then I use another push-pull operation to fill the void and fillet a round corner. I will repeat the same process for the rest of the bracket using direct modeling tool like push-pull and manipulate command. One very useful function I relied on this modeling process is the slice tool. With just 2 clicks, you can slice a solid using a plane, a face, or even a 3D curved surface. The manipulate tool is also very useful for adjusting face angles, and I have used it extensively throughout this modeling process. Most of the modeling time was spent on the side bracket. It's not particularly difficult to model, but it contains a lot of details. Next, I will create a trim curve on the XY plane and use the surface extrude command to generate the trim surface. Then apply the slice tool to cut the side bracket into shape. Now I'm finalizing the details of the side bracket. There are quite a lot of them, but none require special attention to model. Next, I will mirror the left side of the bracket to the opposite side and then modify it to fit. Here is an important step. I'm going to create ribs that run along the edge of the opening, positioned directly on the curved panel surface. First, I will trace the sketch for the opening and define the ribs profile. Next, I will extract surfaces from the back side of the panels. Then I will use the stitch command to weld the surface together. Then I will extrude the rib profiles downward, extending them below the surface. Then I will slice the solid with the surface and keep the lower portion. Next, I will extract the surface from the top slice solid. This surface rests exactly on the back side of the panel. Then I will stitch the extracted surface and thicken it to the required thickness. Then I'll use another sketch to cut open the panel. I will repeat the same process for the next opening. This is how you can quickly create lip lines that follow the curved surface. In Autodesk Inventor, you can project sketches directly onto curved surfaces, but in BricsCAD, the workflow requires a few extra steps. This pocket lies on a different plane, so I will use the 3-point UCS and snap it directly onto the point cloud to create a sketch plane. I will extrude cut the opening, then extrude the wall. After that, I will subtract it from the panel body. I will extrude a solid to close the bottom of the pocket, then cut out the mounting profile. Then I will use a sweep profile to round the corner. I will create a line parallel to the LCD bracket and align the UCS plane to it. This step is important because it prevents the screen from tilting in the wrong directions. Next, I will create a sketch on this plane to cut out the panel. Then I will create the box frame and use the panel to trim it out. The bottom of the bracket is curved on both planes, so I will use one sketch for the sweep profile and another for the sweep path. I will sweep the surface and use it to slice the wall into shape. I will copy the curved surface, move it downward and use it to slice the solid, creating the curved wall. Next, I will extract the surface from the curved wall and use it to slice another solid profile. Now I'm creating the LCD monitor standoff. For the dropout, I will create a loft body and duplicate it, one for union and one for subtraction. I will align this clip by orbiting the viewport and locking it with the UCS view command, then create the sketch profile. BricsCAD has a separate command that lets you extract the body and delete it in a single click. So modeling clips is very fast in BricsCAD. After mirroring half of the panel, I will union the two halves together to create a single solid. Now the model is complete and ready for 3D printing. In the slicer, I just keep adjusting the angle. There is always one orientation that gives the fastest print with the least support. Then you need to inspect the printing layer for the fail support. For the filament, I recommend ABS or ASA because they are easy to sand and offer a good heat resistance. This print took 19 hours and used 385 grams of filament. It took me about 15 minutes to remove the support, and here is the result. The front face looks fine overall. There are a few printing defects, but since this part will be painted, that's not an issue. You can apply filler to the front surface, sand it smooth, then finish with a few layers of the primer and top coat. The backside that faced the supports still looks fine. I accidentally broke one of the standoff, but the rest remain intact. After painting, this print can really serve as a replacement part. It feels sturdy when twisted thanks to the console bezel sticker wall compared to other I have worked with. I won't be demonstrating the filler and paint job this time because of issue with my neighbor. Instead, I print this part just to show how it looks straight out of a regular desktop FDM printer. It feels sturdier than I expected. Here's my workflow for reverse engineering a console bezel. Thanks you guys for watching. I'll see you in the next video.